afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Dr. Carlos Avendaño. He currently holds the position of Senior Lecturer in Chemical Engineering at the University of Manchester. Avendaño has great interest in the modeling of materials at different time and length scales using computer simulation techniques. He acts in the multi-scale modeling group that develop and use modeling and simulation tools to address major research challenges from the fundamental understanding of novel phenomena at atomic, molecular, meso, micro, and macroscopic levels to the prediction of industrially relevant fluid properties and equipment performance. He has accumulated experience in the topics of self-assembly of anisotropic colloidal particles using computer simulation techniques, working with Professor Fernando Escobedo at Cornell, in the development of coarse-grained models for phase equilibrium calculations and studying the self-assembly of non-conventional despotic liquid crystals using computer simulations, working with Professor Eric Miller, George Jackson, Amparo Galindo, and Claire Adjiman at Imperial College, London, and in the development of computer simulation methodologies for ionic systems, working with Professor Alejandro Gil Villegas at University of Guanajuato, as demonstrated through 42 publications since 2006. Welcome, Professor Avendaño. Thank you so much for being here. Please feel free to start your presentation.
Thank you very much, Yuri. Yuri, can you see my mouse by any chance? Yeah, thank you, fantastic. Thank you very much for this very kind invitation to Federico and the organizers. I was talking to them before the beginning of this seminar, and I think the initiative of organizing this webinar is absolutely amazing. So bringing the community together, I think has been great with this activity. So thank you very much for including me in this series. I was thinking to talk a little bit on phase equilibria before, but I saw that my colleagues, Amparo Galindo and Eric Mueller, gave excellent talks on SAFT and coarse graining. So I decided to present something completely different. And I'm going to talk about self-assembly of colloidal particles, and particularly when the particles are constrained in small spaces. And this is by the use of geometrical confinement. So the first thing, this is probably common knowledge for most of you, but I will just introduce what self-assembly is. And in self-assembly, basically you have a collection of particles. They could be atoms, they could be molecules, they could be colloidal particles. And if the correct conditions are present, conditions such as temperature, concentration, and so on, it is possible that the system will form a spontaneously ordered structure. The type of driving forces to get the formation of these structures are typically non-covalent interactions, so van der Waals or electrostatic interactions. Now, the final structure that you get typically depends on the features of each of the individual particles. So what is the way that they interact between each other? What is the properties of the solvent in which they are suspended? And even what is the shape of those particles, which is what I want to talk today about. Depending on what is the shape and all these conditions that I was talking about, different systems can exhibit different type of morphologies. So for example, we know that at low densities or high temperatures, systems tend to form what we call the isotropic phase, where the particles are completely located randomly in the system and they can adopt any type of orientations. The other extreme is when they form a crystal structure. In this case, the center of masses of each of the particles are localized in specific lattice sites. And we can see that the orientation of all the particles are also well-defined for all of them. However, there are several systems, particularly when we talk about non-spherical particles that can exhibit some structures that are in between the isotropic and the crystal phase. Some examples are for the liquid crystals, in which we can see that there is no translational order. So the center of masses of the particles can be in any location within the sample, but in average, the particles are oriented in a given direction. Or we can have another type of structure called a plastic crystal. And here is the opposite of liquid crystals. So now the center of masses are perfectly located in lattice sites, but the rotation of the particles can be completely random. So the particles are able to explore every type of orientation in the system. Self-assembly is obviously the mechanism that nature uses to create functionality. So everything that works in a human body is driven by, in great extent, is driven by self-assembly. These are just a couple of examples of the formation of surfactants. So at the bottom, I borrowed some images from the group of Mike Klein in Temple University, where his group uses coarse grain modeling to get to obtain properties of surfactants and phospholipids. And on the left-hand side, these are just some examples of typical micrographies of the scales of different insects. So every time that we're looking at an insect and see these beautiful colors that can be having generated by years of evolution, that it could be either to attract mates or for protection against predators. Those have been formed by self-assembly. So you can see each of these scales are formed by colloidal particles at the micrometer scale. Nowadays, scientists have been borrowing some of these techniques from nature to try to create synthetic materials, and self-assembly is one of the most efficient techniques to do that. That's a nice way to explain all of this, but in reality it's more challenging, and I will try to explain later on some of the challenges that people typically face when they want to use self-assembly to form materials. There is an advantage of using colloidal particles for self-assembly. One is obviously that they are ideal candidates to create materials in the micrometer scale. So it's difficult to get materials in the micrometer scale just from molecules, but with colloids it's possible. And some of those materials have specific properties that I will talk later on. But the other advantage of colloidal particles is that it is possible as well to tune or modify the interparticle interaction. There are different ways to do this. For example, by surface functionalization. So we can take a colloidal particle and try to coat the surface of that particle with a polymer or any other kind of agent. It is also possible to change the interparticle interaction by changing the properties of the solvent. It's also possible to add certain amount of polymers in the solution to create some depletion interactions. If we have ionic systems, well, adding certain amount of electrolytes to modify the ionic strength will be also, it's also possible. And obviously the dielectric constant of the material is important. So for example, you have a system in which the dielectric constant of the solvent matches the dielectric constant of the particles, then you can minimize the van der Waals forces, and then you can approach even the limit of hard particles. So particles that do not attract, two particles do not attract each other, but they cannot overlap, essentially. Depending on all these factors, and the resulting pair interaction can have a huge influence on the final phase diagram. Just to give an example of how sensitive the phase diagram can be to the pair interaction, this is what we call the Mi potential that probably Eric and Amparo introduced in their seminars. This is a type of Lennard-Jones potential with the only difference that you can change the repulsive and attractive exponents. When n is equal to 12 and m equal to 6, what you recover is the Lennard-Jones. But in this case, I'm showing you an example of a pair potential where n is equal to 24. So it's more repulsive than the normal Lennard-Jones, and that will produce the black curve. If we run some computer simulations, in this case, I use some free energy methods to obtain the phase diagram. This is the typical phase diagram that you get, where you can have coexistence of vapor and liquid in this region. liquid and solid in this region here, and even the vapor and solid. And this kind of phase diagrams can be also observed in colloidal particles. The only difference is that what we call a vapor is actually a liquid phase, which is poor or doesn't have as many colloidal particles as the other coexistent liquid on this side. But what happens, for example, when we make the exponent equal to 48 and let's say m equal to 12? So we can make this potential to be now short range. It has similar form, but the range of the attractive part is reaching just 1.4 in these units. So it's a much shorter per interaction. And if we compute the phase diagram with free energy methods, this is the typical phase diagram. So we can see that the vapor-liquid equilibrium completely disappears. What happens in reality is that that vapor-liquid equilibrium becomes metastable and typically is embedded within the fluid-solid coexistence. But the only stable phases that you observe are typically the fluid and solid. This is something that for a long time has been studied. This beautiful work by Ten Wolde and Dan Frenkel in Science in 1997. It was one of the pioneering papers on this area because this is extremely relevant for the area of protein crystallization. How to be able to remove the vapor-liquid coexistent region to get it embedded within the fluid solid, and that will create a lot of density fluctuations that can enhance the formation of crystals in proteins. So this is a very important topic. But you can see that just sometimes changes in the pair potential can change completely the phase diagram of this system that you have. If on top of that, we add the complexity or the variable of the particle shape, well, things become even more complicated now. So during the last 30 years, there has been an amazing revolution on experimental techniques to produce particles with almost any shape that we can imagine at the moment. So I'm going to talk about 3 experimental techniques, not because maybe they are the most relevant, but at least there are some that I'm using mostly for my research. One is the technique of lithography that was reported by the group of Thomas Mason in 2007. Imagine that you have a substrate, just a kind of a disk. And on top of that disk, you put a monomer. That monomer, as soon as it's exposed to UV light, it will start to polymerize. But before exposing the sample to UV light, maybe we can put a mask with a particular shape that we want to achieve. And using that technique, it is possible to get platelets or particles with almost any shape that we want, as soon as we have a template for that. So these are some examples of that Thomas Mason reported from this paper, going from different polygons like triangles, pentagons, this sort of crosses, and even they managed to obtain the entire alphabet with this technique. And they are just highlighting UCLA because this is the institution where they work in California. Another type of technique is what is called the swelling and phase separation technique that has been developed by the group of David Pine in New York University. Something that is quite, or has been known for a long time is how to create colloidal particles with a spherical shape made of polymers. But imagine that you take some of those particles, for example, this one is polystyrene, and you put it in a solution of decane, and you increase the temperature a lot. So what is going to happen is that the particles will swell, so they will increase in size. But then you can drop the temperature at different degrees. You can do it very quickly, or you can do it in a different stages. Something that could happen is that inside the particle, there could be a phase separation between the particle and the solvent that you have. And with that, you can essentially, by stresses, you can just modify the original shape. And with that, you can create, for example, spherical, these particles in which you have removed a certain section, or even you can create particles that look like bowls. So that is completely controlled by how the temperature is dropped. Obviously, if we change the original particle, rather than being spherical, we have something like a cubic shape or ellipsoidal change and so on, where you can get different kind of particle morphologies. And another way to also achieve non-isotropic particles is by using spherical particles, bring them together somehow, in this case by using similar techniques as the swelling and phase separation technique. But once that they are together, well, they can be polymerized, and with that, different kind of objects can be created. Now, for colloidal particles, one of the final structure that you obtain, obviously everything is dictated by how they interact and by the conditions and so on. But the actual morphology of the particles is dictated by how well they can pack. It becomes really an optimization, one mathematical problem of how to optimize the packing of certain objects, which is easy to say, but even for the simplest shape that we know, which is the sphere, the most efficient packing, it's not an easy thing to obtain. We know very well the Kepler's conjecture that he proposed that, that the maximum packing of spheres is about 74% what you can obtain. But really took almost 4 centuries until Thomas Hale, which is pictured here with these oranges, managed to prove that that was actually correct. And that was only for spheres. But what happens when we have particles that are not spherical, and they could be just, for example, even small deviations from spherical shapes? For example, in this case, if we go to the supermarket, we know that the concept of packing is something very common for all of us. Here we have some apples in which we know that the top and the bottom are slightly flat, but just that small change from the spherical shape will be enough to be able to pack the particles in a different way. And even if we have more anisotropic particles like these Convex and so on, well, the packing will be completely different. So at the end, everything becomes to be expressed as a mathematical problem where we are trying to minimize the free volume of the system. So this phi here is basically the function that represents what is the packing of the particles subject to certain constraints of space and given certain positions of the particles and certain orientations. There are different techniques to obtain that minimum, but Monte Carlo techniques are obviously one of the best methods to do that. So I'm going to talk today about Monte Carlo simulations to obtain the packing of some objects. So in this case, since everything is dictated by packing effects, so we can blame entropy, because entropy is what is going to promote the formation of some of these ordered structures in self-assembly. And back to this picture that I showed you at the beginning, where we have the transformation from this isotropic phase to this crystal phase. And I mentioned before that this typically is a reversible process. So you can go from the isotropic phase to the crystal phase if you have the correct conditions, but in principle, you should be able to go back as well, because everything is driven by simple intermolecular interactions like van der Waals electrostatic interactions. In reality, that doesn't happen always. And the reason of that is because this transformation is typically a first order phase transition, where in order to form the new phase, which is the most stable one, in this case, the order phase, you need to first, the system has to form nuclei of the new phase, which have to grow. But every time that you create a nuclei, a new surface is created. And that we know that nature doesn't like surfaces, and that will have an energy penalty. At the end, the resulting effect is that you will have a free energy barrier that has to be crossed before being able to get the most stable structure. This could be a problem because a lot of the particles that have been synthesized haven't been able to be used for self-assembly. However, there is always a possibility to reduce this free energy barrier. And one of those possibilities is by using what we call directed self-assembly. In directed self-assembly, basically we use an external field to try to modulate the forces between particles such that this free energy barrier can be decreased. Typical external fields that we can use, well, gravitational field. If the particles are heavier than the solvent in which they are suspended, where we will observe a sedimentation of the particles to the bottom of the container. If the particles are either magnetic or electrical, well, we can also use electric and magnetic fields to manipulate the interactions. Something also quite common is to use optical traps to try to guide particles to specific positions. Shear is also important. So you have a sample and you apply a certain amount of shear. Sometimes it's possible by that to induce the formation of certain structures. And what I'm going to talk today is about geometrical confinement, where the particles are confined in a small space by, for example, having a slit pore or any kind of a wall that will constrain the movement of the particles in one of the directions. So I'm going to talk today mainly about geometrical confinement. There are plenty of examples in the literature. So these are some representative papers. This is the one by the group of Mayor and Dijkstra, where she studied the system of hard spheres confined between two hard walls. You can see that at these conditions it's possible to obtain the coexistence between solid phase, which is given here, and these are just the density fluctuations, so density profile, in coexisting in the middle with the isotropic phase. This is a paper by the group Amparo Galindo, where they studied platelets as well, confined between different walls. But another type of confinement is also possible when simply the particles sedimentate to the bottom of a container, and the particles are absorbed there, and they can only move in 2 dimensions. So they can move in the X and Y direction, but they don't move anymore in the Y direction. So that's a different type of confinement, which I'm going to discuss today about. Okay, the first part of the talk, I'm going to discuss the self-assembly of something called convex objects. The difference between a convex object and a non-convex object can be illustrated with these 2 figures. When you have a convex object, you can take any 2 points within the particle, and if you draw a line, and that line is always inside the particle, that's a convex object. Typical convex objects will be spheres, cylinders, ellipsoids, polyhedra, and so on. The difference with a non-convex object is that you draw a line between 2 points and that line leaves the body. Well, that's by definition a non-convex object. And typical examples will be rings or will be particles that are bended and so on. So I'm going to talk first about packing of convex objects. So the first example is a project in collaboration with a group of Czechia leaders in the material science department at Cornell University. So Czechia is an excellent experimentalist, and she synthesized these kind of particles. They look almost like a mushroom cap. So you can see that has a section that looks almost spherical, but at the bottom is flat. If you look at this particle from the bottom, where you will see that flat facet, it has a small dimple, but that's not relevant at the moment. But if you look at this particle from the top, well, essentially what you see is almost like a sphere. So depending from which point of view you look at that figure, at that particle, it could look like a sphere or could look like a non-spherical particle. And that has a lot of consequences, particularly when you analyze these particles in confinement. So Czechia did or used this experimental setup where you can have 2 microscope slides, the typical microscope slides that you use in the lab. You can create a wedge with a certain angle, and then you can inject a sample of the colloidal particles in that wedge. The advantage of this is that the particles would start migrating towards the wedge. And in one single experiment, you can analyze what happens at very strong confinements when you can have only the formation of a monolayer, or you can also move towards the other direction and analyze what happens when you have bilayers, 3 layers, or even more layers. So in one single experiment, you can extract all the phase behavior of these particles as function of the strength of the confinement. The kind of structures that the group of Czechia leaders observed are these ones. I'm going to discuss in more detail what they are. But when she came to talk to Fernando Escobedo and to me about these experiments, The question that she had is, are these structures that she observed in thermodynamic equilibrium, or are they just kinetically trapped structures? That's not something cannot be easily answered just by the experiments, but with computer simulations, we can do something, we can create a model and try to explore the different variables to try to observe if the structures are in thermodynamic equilibrium. So for that, we need obviously a model. And the model that we decided to use, it was a very simple one, albeit a little complicated to model. But we took a hard sphere, so a particle that doesn't have any attractive interactions. But then we took the particle and we cut the sphere at a certain height. So you can see that the resulting particle has the main features of the experimental system. It has a spherical section on the top, but at the bottom, it has a flat facet. And we use that model to study or to try to represent the experimental system. Fortunately, we also have a reference system. So several years ago, the group of Major and Dijkstra reported the phase behavior of spherical particles confined between two hard walls. And the type of structures that you observe are things that you will, just by playing with the spheres, you know that you will form under very strong confinement when the particles can be only constrained to moving in 2D because they cannot move in the Z direction, but they can move on in the plane. You know that at high densities, they don't have any other option but to pack in a hexagonal lattice. That's the best packing that you can get. But as soon as you start increasing the distance between the two plates, the two walls, well, particles will start adopting different type of positions. And with that, they can form monolayers, bilayers, 3 layers. And typically they alternate between having something like a square symmetry with something that has triangular or hexagonal symmetry. So at least we have a reference system, which is the spheres, to try to compare what happens with the non-spherical particles that we want to study. If you have done Monte Carlo simulations of hard particles before, you know that the most important component of the simulation is the overlap algorithm. So every time that you propose a move in Monte Carlo, either by translation or by rotating a particle, you need to check if the new move will lead into a configuration with overlaps or not. If there are not overlaps, you can accept the configuration, and then you keep repeating that over many cycles. If the configuration that is proposed leads to an overlap, you just reject the move, and then you start proposing a new move and so on. We decided to decompose this particle into 2 objects. We can model this non-spherical particle as being formed by a spherical shell, which I'm representing here, and is capped by a flat disk at the bottom. So essentially with 2 objects, we can model the particle that we want. And the reason why we did that is because the individual overlaps between disk and bowl have been reported before. So Dan Frenkel reported many years ago the overlap between 2 circular disks, and it's a very efficient algorithm. The overlap between 2 bowls has been also reported by Major and Dijkstra. And Fernando Escobedo and I developed the overlap between a bowl and a disk. And between a bowl and a disk with a hard wall, well, it will be very similar to the bowl and the disk as well. So we have all the elements for the model. And with that, well, we were able, using Monte Carlo simulations, to obtain the phase diagram for these particles. So on the x-axis, I'm showing you H, which is the separation between the 2 walls in which the particles are confined. And in the y-axis, we have the vacuum fraction. So this is the volume occupied by the particles divided by the total accessible volume. So what we observe at very strong confinement, so at very strong confinements, the particles cannot rotate. They can only move in 2 dimensions. And what we observe is that the system forms this hexagonal lattice. This is very similar to what you will observe with the spheres. And it makes sense, because if you look at two particles that are close to each other, the flat facets, they don't see each other. They will only see the spherical shells. So the particles effectively think that my neighbors are spheres. So they should pack in the same way as spheres will pack. And that's what we observe here. The only difference now is, since the particles are non-spherical, the particles can adopt two types of orientations, either the flat facet pointing up or pointing down. And what we observe is, from the Monte Carlo simulations, is that the population, it's 50-50. So we have half of the particles pointing up and half of the particles pointing down, which is exactly the same that was observed in the experiments. Now, as soon as we increase the distance between the two hard walls confining the particles, it makes sense that some of the particles will be pushed up and some will be pushed down once that we increase the density in the system. And that's what we observe here. This is what we tend to call the buckle phase. And it's buckle phase because it forms some sort of undulations along this direction, which were again in agreement with the experimental observations from the group of Chekesha leader. Now, something very funny will happen when we increase the distance between the two plates to be compatible to the size of the cross section of these particles. Now they will be able to rotate. So this is the first time that the particles will be able to rotate. And what we observe is that they don't want to adopt anymore the configuration of either pointing up or pointing down, but rather the flat facet is pointing parallel to the confinement. So this is what the experimental is called a side phase. And again, that structure is completely in agreement with what they observe in the experiments. And if we keep increasing the density of this system, so we move from that point to this density over here, what will happen is that the two particles in this side phase will come together, the two flat facets will align to each other, and they will form this kind of dimers that eventually they can also form a more ordered structure. In this case, they form this Herring-Wong structure. And well, once that we increase even more the distance between the two walls, so we decrease the degree of confinement, we recover again, we start observing the first formation of Valle layers that again, it's similar to what you will observe with spherical particles. And this is again in complete agreement with the experimental observations by Chekesha leader. So far we are observing that indeed the experimental structures are in thermodynamic equilibrium as proved by the computer simulations. After we have a square Valle layer, if they are spheres, we will expect to have the formation of the hexagonal Valle layer once that we increase a little bit more the distance between the particles. And indeed, that's what we observe. And again, that's in agreement with the experimental observations. But now things will become very interesting. If we increase the separation between the two plates a little bit more, and we give again enough space to the particles to rotate, they will do it. And they will do it in a very interesting way. If you look at this particle, at the center of mass of these particles, you will see that the particles are actually located in a hexagonal lattice, the same hexagonal lattice that we have here. So you can see quite clearly the formation of these stripes. But the difference with this structure on the left-hand side is that now the particles actually can rotate. So this is the example of a plastic crystal in which the center of masses are completely localized in specific lattice sites, but the particles can adopt any type of orientation that they want. And if we keep increasing the distance between the plates, now the particles again will try to adopt the side orientation that was observed in the monolayer. And that again is completely in agreement with experimental systems. And we observe again at higher densities that these particles tend to form dimers again, which will form more complex crystals. So you can see how by doing a small change in the particle shape, going from a sphere to something in which we remove a small section, was enough to make this phase diagram extremely complex. But this has an advantage because you can create crystals that do not have spherical symmetry. And for applications such as photonics, that's an advantage. Typically, what you want is to have crystals that do not have any symmetry, but they are in the Fourier space. It's not possible to get it with simple spheres, but with this kind of particles, it's possible. We said, okay, we already analyzed the particle that looks or resembles the experimental particles, but since we had the code, we could explore as well what happens when we decrease even more, or we cut the sphere at different heights. And with that, we observe similar kind of phase diagrams. The interesting thing is when you work only with half of the sphere, so with what we call the hemisphere, the monolayers are not observed anymore. And this system tends to jump from 2 layers to 4 layers and 6 layers, and it always goes in pairs. But again, this is the behavior that we can study with the computer simulations. I'm going to jump this. I'm going to go quickly, but with my PhD student, we also decided to use the same algorithm to study the structures in bulk. So I'm presenting mostly the results with confinement, but just wanted to say that we also explore the formation of the systems in bulk, and using free energy calculations, we managed to obtain the entire phase diagram as function of the height at which we are cutting the particles. Okay, a second example, it's with the confinement of platelets in 2 dimensions. These platelets that I'm going to show you were synthesized using that lithography technique of Thomas Mason that I mentioned to you before. And essentially what Thomas Mason did is to create these particles. He suspended the particles in solution, and by adding a certain amount of polymer in the solution, that will push the particles towards the bottom. So they are not going to have any possibility to rotate. They will be completely absorbed on the substrate. Therefore, they can only move in 2 dimensions. And if we put this sample to a certain angle, well, the particles will start sedimentating to the corner of the container. So as soon as that angle is not very extreme, maybe something like 5 degrees, we will be able to analyze in the same experiments the different phases that are formed as function of concentration, with the bottom having the most concentrated phases, then in the middle the not as concentrated, and at the top the most diluted phases. So again, in one single experiment, it's possible to obtain all the phase behavior for these systems. Now, if we talk about square particles, the first thing that we will think is, okay, they should form square phases. Is what the logic is telling us. If you have square objects at high densities, they should pack as simple squares. However, in the experiments, they didn't observe that. In the experiments, they observed the formation of 3 phases. At low density, so at the top of this sample, they observed the formation of the isotropic phase. We can see that in the Fourier space, the density correlations are completely forming a ring, which is typically what you observe when you have an isotropic phase. But at intermediate concentrations, what they observe is the formation of a random hexagonal phase. So you look at the center of masses of these squares, they are localized in a hexagonal lattice. But the particles can adopt any type of orientations within the plane. And the formation of that hexagonal lattice can be observed also from the scattering experiments, where you can see the formation of these hexagonal Bragg peaks that basically indicate the formation of that hexagonal phase. And at higher densities, so at the bottom of that sample, what you observe is the formation of that, of a rhombic phase. These 2 phases do not make any sense. If you just think about squares, do not make any sense. And this particularly, we have as well this simulation by Dan Frenkel that he carried out in 2004, where he actually observed the formation of the isotropic phase, but at high densities, he observed the formation of the square phase. And in between, he also observed the formation of something called a tetratic phase. So the tetratic phase is essentially a particle or a phase in which each particle has neighbors that arrange in a square fashion, but that arrangement is not propagated in all the space. It's locally speaking, they behave like squares, but in long range, there is no order. This makes more sense for this kind of particles. So why the disagreement between the two systems, the experimental and the theoretical system? One possibility, which was explained in the paper by Thomas Mason, is that if you look carefully at these experimental particles, they are not completely sharp. There is a small degrees of roundness in the corners. And the question is that enough to actually disrupt the phase behavior? Where we decided to study that by a simple model in which we can have, we can change continuously between having a disk to a perfect square. So the model to do this, Charles and Federico will be quite familiar with this. So we decided to use the model of a spherocylinder. The algorithm, the overlap algorithm for a spherocylinder is relatively straightforward. So something, this model is completely characterized by the length of the cylinder, something that you tend to call the aspect ratio. So that's the length of the cylinder divided by the diameter of the cylinder. When the aspect ratio is equal to 0, so when the length of the cylinder is equal to 0, then you have a perfect sphere or perfect circle or perfect disk. Or when the aspect ratio is very large, basically you have almost like a line. So what we decided to do is to put 4 of them together. And by just changing the aspect ratio, we can go between, or we can map between the perfect disk to a perfect square. The void in the middle is not relevant for two-dimensional systems because the particles, the neighboring particles are not going to see that hole in the middle. So we can avoid having to deal with that. Using this model and using computer simulations in Monte Carlo simulation GNPT ensemble, we managed to get the entire phase diagram. The first thing that we did is to check, obviously, that the model reproduces the two extremes, the perfect disk and the perfect squares. And we observed that the model reproduces that. So we observed that the perfect disks form the isotropic phase and the hexagonal phase. And for the case of the perfect squares, we see that at low densities, we form again this isotropic phase. At high densities, we observe the formation of the square phase, where you can see that the structure factor or the Fourier transform of the density distribution, it gives you the perfect peaks in the lattice. And in between, we observe the formation of that tetratic phase that I was talking before, where you can still see the square symmetry, but the rings are, or the peaks are not very defined. They are actually diffuse, telling you that the correlations decay very quickly in space. So we had the two extremes completely characterized. Now we are in the position to study what happens in between. And what we observe, first for this particle here, is quite rounded. We observe the first low density deformation of the isotropic phase, but then this will transform into this hexagonal phase. So the particles have a square symmetry, but now we can see that that small deformation or that small a change in the sharpness of the corner was enough to disrupt the formation of the square phase. And we observe the formation of this random hexagonal phase that if we keep increasing, so here we have pressure against density, if we keep moving in this direction and increase the density, now we will observe the formation of the rhombic phase, which is in agreement completely with the experimental observations. So this allows us to conclude that that small change in the particle shape from the corners of the particle was enough to disrupt the phase behavior. We also analyzed squares in which the sharpness of the particles or the corners is this is a little higher than this system. And we observe exactly the same as the experiments. We observe formation of square faces, but also the formation of the rhombic faces. So again, this is just an example of how small changes in the particle shape could change completely the phase diagram of the systems. Okay, the next example is something that I worked with Eric Mueller and George Jackson. And in this case, we were not interested in understanding the effect of the hard walls on the phase behavior of the system. Rather, we wanted to use the hard walls as a tool to study the phase diagram of a system that was complicated to study in bulk. So what I'm trying to say with this is the following. We wanted to study the mixture of cylinders with spheres. That's a system that has been studied experimentally a lot. But from the simulation point of view, it's a very complicated system to deal. The reason of this is the following. Typically, when you have a pure component system, for example, these cylinders, you can run a simulation where you have your particles in a box, and then you can run a simulation in the MPT ensemble. You keep increasing the density of the system and observe the transformation of the system. When we have binary mixtures, we know that we cannot do that. So you think just in the typical phase diagram of a binary mixture that we tend to study in chemical engineering. So you have something like a hexane or a mixture of alkanes. You know that as soon as you enter into the phase coexistent region, the system will split into two phases, but each of them with different compositions. Therefore, it means that we cannot use the same technique as pure components. So we cannot just simply put a mixture with a given concentration and increase the density. We have to allow the system to separate into phases with different compositions. There is a technique called the direct coexistent method, where you can actually put molecules or colloidal particles in a very elongated box like this one. And as soon as you have the conditions for phase separation, the phase separation will happen or will take place. And that's a typical technique to obtain phase diagrams for mixtures of liquids and so on. However, for this kind of systems like cylinders and spheres in the colloidal regime, the problem is that you do the same technique, you are not going to observe the segregation between two phases. Despite that thermodynamically you should observe that, it's not possible to observe that in reality. And the reason is because the surface tension of this system is so low that it's not possible to form a perfect interface between two phases that are being separated. So that was a problem because we wanted to obtain the phase behavior, but we knew that the technique wasn't working. So what we decided, and there was an idea from George and Eric, is maybe we can confine the particles between two walls. That will create enough surface tension for the system. And then we can analyze what happens in the middle of the sample. The system still will have chance to segregate or change in composition along this direction, but at least the system will be stable now. So we decided to use geometrical confinement as a tool to study the phase diagram of these systems. And these are the results. So in this phase diagram, so on the x-axis, we have the vacuum fraction. In the y-axis, we have the pressure. And we can observe that as soon as we increase the pressure, the density also increases until we observe the transformation from the isotropic phase to something called the nematic phase, which is given here. And even at higher densities, we should observe the formation of the smectic phase. Just with this simple technique of adding two hard walls far away from or having a long system and the walls being far away, that means that we can have a bulk region that we can use to characterize the system. And we did it for the pure components, which is the results here at the top, but also we did it for the mixture between the cylinders and the spheres, and the phase diagram is here. So without going into too much details, the only thing I wanted to show you here is that geometrical confinement can also be used as a technique to study the phase diagram of systems that are intrinsically complicated to study because the surface tension is very low. Finally, the last example of convex particles that I want to show you, it's a project that started as a collaboration with AstraZeneca. One of the main problems in the pharmaceutical industry is the step of filtration. So let me explain you better what I'm trying to say with this. In the pharma industry, first, you will have your reactor and you will synthesize whatever API that you are interested, API that you are interested. And after you create the specific molecules that you want, then you have to purify them. And the most common technique to purify APIs is basically by crystallization. So that after the reactor, we will have the crystallization step. And after that, we need to remove the solvent in the system. And that's typically done by filtration. So we put it in the reactor. We have a filter at the bottom of the reactor. And then by having a vacuum pump, we can create a pressure drop. And then all the liquid will disappear. However, this filter cake formed here has a certain degree of porosity. And most likely a lot of the solvent that typically these are very harsh solvents that you need to completely remove if you want to put these kind of particles in tablets for human consumption. The problem is that we need to remove that solvent that is trapped. Therefore, we need to do a series of washes to do that. That's one of the most expensive steps in the pharma industry. And it's expensive because typically these filter cakes have very high density. So something that the pharma industry is interested in is there a way to manipulate the porosity of those filter cakes? Ideally, they want a filter cake that will be will have very high porosity. In that way, when we do the series of washes, the liquid can be transported across the network easily without much resistance. And the amount of time invested on the washing step will be reduced. So that was the PhD dissertation of this excellent student, Giulio Perini, who is working now for AstraZeneca as well. He did a lot of experiments with glutamic acid and other molecules that typically they form needles. So this is the image that we obtained from X-ray tomography of one of the crystals. Typically, these particles have different facets. So we try to represent ideally that particle with this image here. And we decided to do the following experiment. Okay, so we know that these filter cakes are formed by this type of crystals, this type of needles, but they have different size and shape distributions. That's something important in the pharma industry. What is the typical length and diameter of these particles? And a typical size and shape distribution of these particles will look like something like this, where in the x-axis you have the different dimensions for this axis, for the width of your particle, and in the y-axis you have the length of the particle. So these are the type of distribution that you have, where the mean or the average aspect ratio is here at the middle. So from the experiments, we have the type of populations for different experiments. Some of them run at different temperatures, some of them run at different pressures and so on. We wanted to have a quick technique to determine for a given size and shape distribution, what will be the porosity that we have. And we would like to have a technique that we could easily manipulate that shape and size and shape distribution to try to find what is the optimum parameters to maximize the porosity of the system. So that's the problem. Given a certain distribution, what will be the porosity that we will get? For that, we actually came up with this very nice paper by Charles and Federico that they published for simple cylinders, only monodisperse and binary systems. But we decided to use the similar technique to study the packing of highly polydispersed mixture of cylinders. And with that, we came up with this phase diagram where in the X direction, what I have is the coefficient of variation of the length of the system. So this coefficient of variation, CVL, is telling me how broad is the distribution along the L1 direction, along the Y direction in this diagram. The higher that coefficient is, the more distribution of lengths in the particles you have, the lower, well, the most central will be to the mean. And in the Y-axis, what we have is the average aspect ratio of that distribution. So the center, this aspect ratio here will be the center of that distribution. For example, for this particular system, the average will be at 400 micrometers in length with about 100 micrometers in width. So that will give you an average aspect ratio of 4. But again, depending on the temperature at which you run the experiment, you could have different sort of distributions. But we decided to use Monte Carlo simulations to analyze the packing of different distributions, and we came up then with these results, where we can observe that to maximize the porosity of the systems, we have to increase the average aspect ratio of the system. So as soon as we move up here, we can see that the maximum porosity is reached around here. So it's kind of, it's maybe logic, but it's clear that the higher the aspect ratio is and the higher the polydispersity is, the higher the porosity should be. The interesting thing here is that we developed this technique to obtain those results in a matter of minutes, because these simulations are not in equilibrium. And basically, we are just sedimentating the particles under a very strong gravitational field. Essentially, they are not colloidal particles. They are mostly granular materials. But those simulations are extremely fast, and we can repeat it several times to get some statistical certainty on the accuracy of the results. But when we compare the results that we obtain from these simulations with the experimental observations, we've observed a perfect matching. Despite that the model is not exactly the same as the real crystal, but just by having a particle that looks or resembles a needle, that was enough to be able to get the results in agreement with the experiment. So for AstraZeneca, that was actually quite useful, because we can now tell them this is the type of distribution that you should have if you want to maximize the porosity of the system. And that's something very good for them, because they know very well how to manipulate this kind of shape and size distribution just by doing things like temperature cycles or just breaking particles with milling and so on. So that's possible to do. What we gave them was just a technique to represent what kind of porosity you can get. I'm going to move very quickly to the second part. I'm sorry, I know that I'm running a little late, Federico. I'm going to go a little fast with this second part. But the next part I want to study, or what I want to show you, is about self-assembly of non-convex particles. And in particular, the aim here is to try to obtain particles that have high porosity. So everything that I showed you before was about maximum packing of objects, something that will give you structures with very high density. But now we want something also the opposite. Is it possible to have colloidal particles that will render a structure with high porosity? And that's something that I've been interested in the last 5 years. One possibility to do that is by using what we call non-convex particles. So these are particles that are highly irregular, and there are several examples in the literature that have been reported recently. They can go from particles that are sort of bended, like imagine taking a cylinder, but now you bend it slightly, or moving to particles that look more like rings or frames, or particles that look like branched objects, and so on. All these particles have a common feature, and that common feature is that the packing is not very efficiently between them. So imagine putting two objects like this, you know that they are not going to pack very, very well. So the idea that we had is, can we take that as an advantage and try to see what kind of a structure we can observe by changing the degree of non-convexity in the systems. There are many examples in the literature if someone is interested in talking about them. But this is just a slide with several papers that have been published recently with non-convex particles. Perhaps the simplest non-spherical, non-convex object that exists in the literature is the dimer. So in this case, this is formed by two spheres that are bonded together. And you can see if you draw a line between that point and that point here, the line will leave the body. So it's by definition a non-convex object. That's an interesting system because the intuition is that the packing of this system should be very similar to the one of spheres. Why? Because the particles are made of two spheres just bonded together. But something interesting happens in reality. It's that in 2 dimensions, we have these dimers, they will have different possibilities to arrange. They will pack almost exactly the same. So the individual spheres will pack exactly the same. But now it depends on how the orientation of the particles takes place. It could be in a very well-defined fashion like this, crystal, or it could be completely random. And something that was reported by Dan Frenkel a long time ago is that this second structure is more stable than the previous one. So this is less stable and this is more stable. What he did is very sophisticated free energy calculations, and he observed that the free energy of the two systems is basically the same. But they concluded that this is a more stable structure because the entropy of the orientation of the particles is much higher. Well, with a group of Czechia leader, we collaborated again, and she carried out the experiments for dimers. And using the same experimental technique of the wedge, she was able to observe the formation of these monolayers and bilayers. The monolayers will be the experimental counterpart from the simulations from Dan Frenkel. And we can observe that exactly the same that was reported in the simulations is what we observe in the experiments. But now, using similar simulation techniques as the one I explained before, we managed to also reproduce the entire phase diagram observed in experiments for different heights. So formation of monolayers and bilayers. And this is the type of phase diagrams that we observe. So again, this is just to show you how with Monte Carlo simulations, we were able to represent the experimental observations quite well. But now coming to more anisotropic or more non-convex particles, one that I'm particularly interested in is in this one that look like rings. The reason of that is because they are objects that cannot pack very efficiently. So something, I'm going to skip this slide. Experimentally, these particles have been synthesized. If someone is interested in the experimental technique, I can talk a little bit about that later. But these particles can be synthesized and they can be used a lot, or they are used nowadays a lot for drug delivery. So you can imagine that encapsulating particles in a spherical object compared to a toroidal object. In the toroidal object, the path that the drugs need to take to reach the surface is much smaller or shorter than the one for the large particle. So in that way, the release of drugs is more efficiently in this kind of objects here. So something that I was interested working with Fernando Escobedo, I was already in Manchester when we were working on this, but collaboration with Eric Mueller, Fernando Escobedo, and George Jackson, we decided to study the phase diagram of these kind of particles. I will show you quickly what happens with a ring like this. So we run some molecular dynamic simulations, starting first from a low pressure or low density system. When we run the simulations, we observe that the system just forms a typical isotropic phase. There is no order in the system. The first thing that we were thinking is, okay, these are very rigid rings. Maybe if we increase the pressure or the density, they will behave almost as discotics. So they will start packing like in a columnar phase, similar to, imagine having coins. The best way to arrange coins is in a columnar phase. So we were thinking that maybe that will happen again here. But what we observe in reality is something completely different. So I'm going to run a little bit, let it run for a little longer. And hopefully at some point you will see that the system starts forming layers. And in each layer, the rings start to try to interpenetrate each other. So what happens is that the particles will try to interpenetrate each other and they will get confined in a single layer. And essentially what they are forming is a smectic phase. But something very interesting with this asymmetric phase is if you look at the packing fraction that you obtain, the packing fraction for that asymmetric phase is about 10%. So we're talking about liquid crystals that have very high porosity. And again, that's a consequence by the non-convex shape of these particles. We decided to do we started to analyze this system even more. For example, we studied different sort of shapes of the rings and also different aspect ratios of the rings. And what we observed it was a very rich phase behavior of these systems. And but the most important thing is that the densities that we observe are always extremely low. Even for this very thin ring that we have here, the volume, the packing fraction that we obtained was about 5%. So basically it's almost empty space in this system. And we decided to analyze this system where they are in confinement as well. So by placing the particles within two walls, something extremely interesting happens. So imagine that you have a coin and you just toss it. What you will imagine is that the ring will try to lie completely flat to the wall. It makes absolutely sense that that should happen. And we were expecting to observe something similar, those rings would start absorbing to the surface completely flat. But similar to this paper by Amparo Galindo, where you can see the particles absorbing flat next to the surface. But what we observed, it was something completely different. What we observed is that as soon as we place the particles and we increase the density, we start observing the formation of these layers, similar to the simulation that I showed you before in bulk. And if we keep increasing the density in the system, they tend to form the same asymmetric phase that I showed you before. But the particles are not lying flat with respect to the surface. They are completely lying perpendicular. And this is because the particles want to form always that asymmetric phase. And the only way to do it is by lying in a configuration that is completely perpendicular to the system. So this is not a normal behavior, but again, this kind of interesting or very weird behavior just arises from the non-convex nature of the particles. We decided to use to confine this to have very large system just to make sure that all these results were consistent, and we observed that. The last system that I want to explain, it's again, coming back to the platelets in 2 dimensions. We said, okay, we understand quite well what happens when we have regular polygons in 2 dimensions. We know how well they pack. There have been a lot of reports about it. But what happens if we transform these particles into the non-convex counterparts? For example, when we modify the edges and we make them slightly rounded, if you want, the particles are not going to be able to interact in the same way. So imagine the case of a square particle. When they come together, the 2 edges will try to align at high densities. But for the non-convex counterpart, that cannot take place. And what will happen is that the particles, rather than being aligned, they will start shifting by a certain distance, because that will maximize the packing between these 2 structures. So we decided to analyze that, that type of systems. First, I will show you the results for the hexagonal, for the hexagons, non-convex hexagons, in which in the x-axis, again, I have the packing fraction, in the y-axis, I have the pressure. We start first at low densities where nothing will happen, so we will have just the typical isotropic phase. But then suddenly we observe a phase transition in which the particles start forming a hexagonal phase. But if we pack even more, or we increase the density even more, we start to observe that the particles will start forming that shifting shifting between the edges of that I was discussing before. That is producing something very interesting. That curvature in the edges of the particles is promoting the formation of a chiral phase, because that shifting between the 2 edges takes place in the same direction all the time. So this is a very nice example of having a system that is not chiral, but promoting the formation of something that has a chiral structure. And again, that arises just by the non-convex shape of the particles. we were able to analyze as well what happens with the square particles, and we observe exactly the same behavior. And we came with a rule that as soon as the number of nearest neighbors around one particle is equal to the symmetry of the system, it will be able to form this kind of chiral structures. But when you don't have that symmetry, well, the system is going to try to pack us in the best way that they can, but the formation of chiral faces hasn't been observed. I think I'm going just to explain this very quickly. So one thing that we also explore is the case of these triangles, or these non-convex hexagons. But in this case, we added attractive interactions. So in this case, we are trying to promote the alignment between two particles. What we observe is that depending on which edges interact with which edges, different kind of structures can be observed. And what we observe, I'm going to skip this very quickly. We observe that the system tends to form some type of hexagonal structures with very high porosity. You can see that there are big holes here because the particles cannot pack very efficiently. But the way that two particles will interact, or several particles will interact, will form these pores or these holes in different symmetry, either forming chiral symmetry or non-chiral symmetry. Something that we are currently trying to study is what happens when to these particles we tend to functionalize them. So we tend to add some oligomers in the different corners or in the facets of these systems. Because of that, with that, we have been able to we've been able to obtain different kind of structures. But these are things that we are currently trying to study, how to keep promoting the formation of these chiral faces, just driven by packing, but also by functionalizing the particles. Okay, I think this is everything I wanted to show you today. The last thing I would like to do is to thank all the people I've been collaborating over the years in this topic. First of all, obviously the most important people, which are the PhD students that are doing always the hard work during their degree. In this case, Giulio Pellini, who is now working in Unilever. Nicoletta, who work a lot in the system of platelets, as well with Junju, who used to also work in a project in collaboration with Unilever. John McBride, who did a lot of simulations of the non-spherical particles as well. And my colleague Andrew Masters in the Department of Chemical Engineering at Manchester as well. My colleagues at Imperial College, Amparo, Eric, and George, which I've been working with them for many years. And they are not only colleagues, they are very good friends. I enjoy working with them a lot. And the same with Fernando and Chakesha Leader. Fernando is someone who I learned so much, and I just want to thank him again for everything that I learned from him. Alejandro, who is my PhD supervisor, that I still had the privilege to collaborate with him, and one of his colleagues, Ramon, who works in the same department. And one of my collaborators in Paris, Rick Wensick, who is the person who is always doing the theories for this type of systems, which become very complex. And obviously the sponsors, so EPSRC, so the Research Council in the UK, AstraZeneca, Unilever. And while I was in the United States, a lot of this work was funded by the National Science Foundation and the Department of Energy. So thank you very much. And I'm very sorry for running a little bit out of time.
Thank you so much, Professor Avendaño. We are now open to questions. If you want to ask one, please, you can feel free to enable your microphone and write questions on the chat. And I would like to remind our YouTube viewers that they can also ask questions on the chat. Professor Fred wants to be the first.
Yes, I
want.
Thank you, Carlos, for this amazing presentation, very rich phase diagrams. It's hard to follow all the details, but was very nice. I'm impressed about the non-convex phase diagrams and possibilities that you are studying. One of those is now you have a tool that you can maximize the area, but keep the very high porosity.
Yes.
That's good. Is going to be very important for reactors and for a lot of chemical engineer equipments that we need high area, but still keep the high porosity of the system.
Yes, actually, something that some of my colleagues are working in Manchester. It's on the design of electrodes. So they want to design electrodes that have very high porosity, simply because in that way you can minimize the mass transport resistance and then use very efficiently all the surface available from these systems. Nowadays, not only these kind of techniques can be used, but also the new techniques of printing some of these materials has been, possible to make porous materials. So imagine using printing of a network, and then you can coat the surface of that network with a certain precious metal for catalysis. That's something that is being used a lot. Some other groups have been also trying to work with this kind of porous networks, trying to check the mechanical properties, particularly when you have structures, imagine something like the Eiffel Tower. That kind of structures at the microscopic scale have completely different type of mechanical properties. And in some cases, they can actually be compressed, but they can be regenerated once that you release them from the pressure. So yes, I agree with you. I think these kind of systems are important. In terms of self-assembly, I think it's a challenge because all these type of particles experimentally tend to have or to create a lot of jam structures, and they tend to be trapped in kinetic traps. So it's a difficult thing to do. But people keep working on this and try to optimize as much as possible the process.
Yeah, that's why I was thinking about the questions. The following question is that how I can imagine that you use molecular dynamics in some example, and I could imagine that it's easier to be trapped in a local minima. A local minimum. You have maybe several minimums in this run, but how you can measure that you are in a minimoid of your configuration? Yeah,
that's a very interesting question. So everything that I talked today was mainly about thermodynamics, but I didn't talk anything about kinetics, and it's a topic that I'm interested to work in the future. There are several techniques that can be used to study nucleation and crystallization of these systems. Fernando, for example, Fernando Escobedo is someone who has been working a lot on nucleation of these systems by using.
He showed something for us. Yeah. He presents something about kinetics for us here, but it's very complicated topics.
It is complicated. The first step, obviously, is you always need first the phase diagram, because typically when you try to study nucleation, you need to make sure that your system is in supersaturation. And depending on the degree of supersaturation, you can have different energy barriers. So the first step is obviously always to calculate the phase diagrams, and then to move into the experiments on nucleation. Now, something I didn't explain because I had to go real quickly, and apology for that. Modeling convex objects in Monte Carlo is relatively simple. You need just to detect the overlap algorithm, and that's all that you need. Non-convex particles are a little more complicated. So, for example, this particle with branches, or particles with branches, is not a problem. This model has actually, or this model has been designed with the spherocylinders. But the case of the rings, and this will be the same problem, you're trying to do some simulations to obtain the phase diagram of something like a cyclohexane. You imagine having two two cyclohexanes and you make a Monte Carlo move, it's always possible, because this is a non-physical move, that they will interlock completely unphysically. Almost imagine taking two rings and interlock them. But that's not possible. How to prevent that from happening in the Monte Carlo code is not simple. You need to somehow devise a mathematical algorithm to prevent that kind of interlocking. When I talked to Philippe Ungerer many years ago about this topic, he said that he had exactly the same problem working with different cyclohexane and cycloheptane, that he couldn't do those moves. For that, in that aspect, it's much better to work with molecular dynamics, because you're not going to have that kind of physical moves and so on. But yeah, that component is complicated. So try to do the nucleation experiments of these non-convex particles using Monte Carlo techniques will be a challenge for sure.
Thank you.
Thank you.
Congratulations.
Thanks. Any other questions?
We have a question on the chat by Professor Richard. Maybe he wants to ask him himself.
Hi, Richard. Thank you for the question. Yeah, so the first question of Richard is, what is the length scale in the particles of Thomas Mason? I'm going to just include them here. So this error bar, if I remember, is about 20 microns. They still, you are always moving almost to one of the extreme of the, what you call a colloidal particle, but they actually observed that there was a still Brownian motion at that scale. So, but yeah, that was about 20 microns. And I think the minimum scale that they presented in the experiment was about 4 microns, if I remember correctly.
Okay, that's much larger than what I was thinking.
Okay, thanks. The system that I show you in collaboration with Chekesha Lidl, the size of those particles are about 100 nanometers. The one with the spherical or the Mostrom caps and so on. The second question is, can this smectic colloidal ring be locked into their shapes, then dried by sintering? Well, that's a very interesting question, and I don't know. There have been some reports nowadays of these rings that I was mentioning before, but so far nobody has been able to observe the smectic phase. If I go quickly to the experimental papers on the rings. Okay. So this is the type of colloidal ring that has been formed lately. The experiment is actually quite fascinating. If you don't mind, I will just explain it in a minute quickly. So what they have is some droplets of nanoclays. So it's something that as soon as you create a shock or a small perturbation in the system, they will form a gel. So they have these nanoclays in suspension, and then they let this droplet to fall on a surface. And you know, you just let a droplet falling on the surface, they will tend to form some sort of toroidal shape. This is something that you can observe from fluid mechanics. So you do CFD calculations, you can obtain that kind of shape. So what they decided to do is, well, maybe in that droplet, we can include these nanoclays. And depending on the speed at which they are falling, they will be trapped in different stages. And they optimize the speed of that droplet to try to get these rings. And they haven't, as far as I know, nobody has been able to observe these smectic phases. And I think the problem is that the type of interactions that I was modeling, which are completely repulsive, is very difficult to attain in colloidal systems. It has been possible to do in spherical particles, but for rings, first, you need to synthesize them. And second, you need to manipulate those forces. And I don't think that has been possible yet. However, it is possible then that people now with printing could do something like that and essentially try to resemble the same structures that are observed from the packing of these objects and just to print them and use them as membranes or something like that. Does that make sense, Richard?
Yeah, I think so. Yeah, I think when you're using a droplet like that, you know, you're working with surface tension on a pretty macro scale. So getting down to the, you know, sub-micron level is going to be pretty tough.
Well, these ones are actually, these ones are sub-micron particles, the ones that I'm showing you here. So they did actually some at the millimeter scale, but they managed to also get them at the micrometer scale. So they're pretty small rings. But again, the problem has been that to try to induce the type of interaction that I was modeling, I don't think it's still possible. So I think that definitely will be a challenge. So unfortunately, at the moment, it's more like a fundamental project rather than still an applied project.
Yeah, I was trying to get below like around 10 nanometers for the ring size because I had a particular interest. You'll see in the fourth question.
Just very quickly, for the micrometer, for the nanometer scale, there has been reports like this, where using some etching techniques has been possible to create perfect rings. In this case, these are gold platelets that have been coated with platinum, I think. And just by using electrocatalysis, they were able to remove completely the gold from the middle. And at the end, you can just get the rings. And another way that lately has been possible to get frames is by using DNA origami. And that's something that recently has been possible completely. But yeah, you can do it either by etching with electrochemical techniques or by DNA origami, at least for the nanometer scale. These are mainly used for catalysis, obviously. At those scales, they will have different catalytic properties. And I think this is why they are very appealing for people working with interaction engineering.
Looks very expensive.
Thank you. The rings can be, okay, yeah. Is there any theory for computing these phase diagrams or only simulations? That's an interesting question, which I forgot to mention that my colleague Rick Wensink has been working with me in trying to get sort of Onsager type theories for the rings at the moment. It wasn't an easy task. Rick is very good on those kind of analysis, and he was able to get at least the phase. He managed to reproduce the phase transition observed in the simulations of the rings that I had. But yeah, using Onsager theory, the problem with Onsager is that you need to calculate the excluded volume between two objects. So what is the excluded volume between two rings is not a simple problem. But he managed to do it, trying to combine basically the overlap between a ring and a disk. And then he moved into trying to extrapolate that limit until basically he had two rings. But yes, we've been working on that. And well, George Jackson and Rick Wensink have been doing all the theoretical calculations. From using other kind of modeling like a DFT, I think that will be a little more complicated at the moment.
Okay, very good. So just stick with Monte Carlo simulation, huh?
Yes. Thanks, Richard.
Thank you. Thank you.
Do we have any questions? Any more questions? I don't think so.
If there are more questions later and you want to send me an email, I will be always happy to answer any questions. Okay.
Thank you, Professor. So I think it's time to wrap it up. I would like to thank you again, Professor Avendaño, for being here with us today. Thank you for this amazing presentation. And we are now headed to the final announcements.